Measures of dispersion. First of all, why is dispersion important? Let's have a look at two stocks, so stock A and stock B. Now you can see their expected return is the same. In other words, over the entire period, so starting from here all the way to the end, their average return will be 10%. But look at the volatility that the two stocks experienced along the way. So if you look at the stock A, the individual returns, which is represented by the red line here, were pretty close to the 10% average. On the other hand, if you look at stock B, you could see that the individual returns had a very wide dispersion from the average. So therefore, while both stocks have the same average return, the individual period returns for stock B are more dispersed. And therefore, stock B's returns are more volatile, therefore more uncertain, and therefore more risky. These three words are interrelated, and that makes perfect sense. If something is more volatile, that means it's more uncertain, and if something is more uncertain, therefore it is more risky. So what I hope this simple illustration demonstrated is that we can't just look at return in our analysis for investments. We also have to look at the dispersion, and clearly stock B is very concerning. Now I can understand if stock B is volatile, but then I would expect a much higher return than a more stable investment. In other words, if I asked you which investment would you prefer, knowing that both have the same average return over your horizon, but one is riskier than the other, I think we would all agree that, if we're going to earn the same return, well, why put up with the volatility? I'd rather go with stock A and earn my 10% in a more stable, consistent manner. So this is very much real life and investment related. So the next question is, how do we quantify dispersion? Let's have a look at an example. Suppose that stock Q exhibits the following returns over the last 5 years. So here they are, annual returns, 8 minus 2, 7 minus 5, and 12. All right. So now what we need to do is we need to measure the dispersion. So now generally the way we measure dispersion, and I showed you here, is we measure dispersion around the average. So that's how we capture risk. The question is, how volatile is the stock around its average? And you can see here that it's very little volatility around the average. But if you look here, that's a lot of deviation from the average. So that is going to be the first step for practically all measures of dispersion. Let's find the average, and then we can measure how dispersed the individual returns are around the average. All right, so the default approach to calculate average is just arithmetic average, which we just add up the values and divide by number of observations, so you have 4. So over the 5-year period, we earned an average return of 4%. And the first measure of dispersion is going to be range. So what range does, it's a very overly simplistic way of looking at volatility. It just looks at the highest value in the data set and compares it with the lowest value in the data set. So the highest value is 12, lowest value is minus 5. So the range between 12 and negative 5 is 17. So how do you interpret that? There's a 17% spread between the highest and lowest return over the last 5 years. Now note, well, first of all, before we move on to the note, you can tell that range really doesn't give us much insight. So if you tell me there's a 17 spread between the highest and lowest, well, how about all the other returns in between? So the only thing range is looking at is it's just looking at 2 observations. So even if the data contained 500 years, or not 500 years, but 500 stocks and 500 individual returns, range would still just look at only 2 data points, the highest and the lowest. So it completely ignores what's happening between these values. And also you'll notice that with range we didn't have to use the arithmetic average of the data set. However, The remaining metrics measure dispersion of returns around its mean. By definition, some dispersions will occur above the mean, while others will occur below the mean. Let's go have a look, right? We have to see it to believe it, right? Here's what we're talking about. Look at stock B, because with stock B, dispersion is more obvious. You have some dispersions above the mean, and the other dispersions below the mean. So these would be positive dispersions, because they're above the mean. These would be negative dispersions. Now here's what will happen. Here's what the notes say. If we simply add up the two, it'll equal to 0, because by definition, the average cuts through the data. But that's not true. So if this isn't 0 dispersion. That's a lot of dispersion. So this would be misleading. Now here's the thing with dispersion. We're not interested in the direction of the dispersion. We're interested in the size of the dispersion. See that? We're interested in the size. We're not interested in the direction. So how do we neutralize the direction of the dispersion? We square the deviations, because when you square the deviation, so if you do a negative square, it becomes a positive. Because otherwise, like I said, if you don't square the negative dispersions, then the sum of these two would equal to 0, and then that would give us a misleading perception of what dispersion really is. So there it is. So as I explained, if you don't square the dispersions, the sum of the dispersions will equal to 0. So therefore, to measure volatility, eliminate the algebraic signs of the dispersion. So there's a number of ways to do it. And before we do that, let's have a look at the tip. And it says, look, because we're interested in the magnitude or the size of the dispersion, not its direction. We covered that. Now, the illustration I showed you up here, where we had positive dispersions and negative dispersions, I suggested that we square, and I did that because that's the most common way to eliminate the negatives. But if you look at our first, or I should say the second dispersion metric, it shows you how else we can get rid of the negative, and that's by taking the absolute sign. So it's called mean absolute deviation, or MAD. And by taking the absolute value of the dispersions, even the negative dispersions become positive. So then there's two ways for us to get rid of the negatives. We can either square them or take the absolute value of the dispersion, so that even negative dispersions, right? So if you have a negative value and you take its absolute value, then it's expressed as a positive. So there it is. Show you the steps on how to do it using our data set. So remember, we found the average first, and then it's just a question of finding the absolute value of the dispersion of each individual observation from that average. So there it is, there it is. And then you divide it by the number of observations, which is right here. In our case, it's 5. So then I show you another step. So from there, we go there, and then you get 6. So that would be the mean absolute deviation. Again, these are deviations. So when someone says deviation, what's the next question that comes into your mind? Deviation from what? And in almost all these dispersion measures, it's deviation from the mean. And you can see that right there. Okay. So now let's look at the more common approach to calculating dispersion. And that is variance. So variance is, again, average deviation of individual observations from the mean. Now notice that it is this framework for variance, the variance framework is very similar here. And I told you what the difference was. There's two ways to get rid of a negative. You can either find the absolute value, or the second approach is to square it. And I want to point that out to you so that you're not having to memorize two different frameworks. You really just need to master one framework. But used differently. Here we find the absolute value of the dispersions. Here we find the square of the dispersions. Otherwise, everything is the exact same. Now, when it comes to variance, we need to distinguish whether we're looking at the population, which represents all observations, or a sample. So why don't we look at a population first? So with population, so the numerator, it's just the deviation of individual observations from the population mean itself, or the population average, and we square them. You know why we square, so that even the negative deviations become positive. Then we add up all these deviations, and then we divide it by number of observations. So that's your variance computation. And so there it is. I show you the steps, and you could see that the numbers in the brackets are the exact same. They're the exact same as MAD, or mean absolute deviation. The only difference is with variance, what we're doing is we're squaring these guys, right? And then dividing it by number of observations. And then I show you one other step. And when you solve this, you get 41.2. Now, after you have found variance, now remember why we squared. We squared so that the negative deviations turn positive. But after you have found this number, the variance, then we neutralize the square by finding the square root. So when you're doing the algebra, you're always doing it in variance. But then when you're ready for the final answer, you bring it back to its original state, i.e., without squaring. So you just find the square root of 41.2, and it works out to 6.4%. So what does this measure? Again, it's the deviation of individual observations from the mean. Specifically, it's the average deviation. Why is it average deviation? Because you can see each individual observation has its own dispersion from the average, or the mean, I should say. So what variance and mean absolute deviation do, they're really calculating, what they're really saying is, look, we have a lot of data points. On average, this is how much they deviated from the mean. And there it is. On average, the annual returns deviated by 6.4% from the mean returns over that period. Now tip, notice we use the same data set for mean absolute deviation and standard deviation, but we got different measures of dispersion. Why is that? Well, with standard deviation, remember that the dispersions were initially squared, so this would give the bigger dispersions even more influence. So when you find the square of a big number, it becomes exponentially larger than if you squared a small number. And that is really the mathematical explanation as to why, for the same data set, standard deviation ended up being higher than mean absolute deviation. So this is with squaring, with squaring, with squaring, and this is without squaring. Now, when you're dealing with a sample, which is just a subset of the population, the only thing that changes fundamentally is the divisor. So remember, with a population, if we're looking at the dispersion of population, the denominator is n, but if you're looking at a sample, the denominator becomes n minus 1. And just very quickly, what's the logic here? So when you're doing n minus 1, the divisor becomes smaller, right? Because instead of n, it's n minus 1. So n minus 1 is lower than n. And therefore this increases, the variance increases. But doesn't that make sense? Because when you're dealing with a sample as opposed to the entire data set, wouldn't you expect there to be more uncertainty with a sample? See how there's a storyline behind the mathematics? Okay, so that's about it. And the other thing that changes is some of the annotations that are used. So if you're dealing with a sample, we use the sample average, which is x bar, whereas if we were dealing with a population, we're using mu. But that's cosmetic. Like that's not a fundamental difference. That's just using a different notation for average, because even here it's average. And the denominator, the n, is referring to the sample size itself. Okay, but the computation is almost exactly identical. So you could see in the numerator, so had the above data set been for a sample, you could see that this numerator is the exact same numerator that we used when we calculated population variance. The only difference is with population, you're dividing it by n, but with a sample, you're dividing it by 4, which is n minus 1. So when you work that out, you get that sample variance, 51.5. But just as we did for population variance, after you have the variance number computed, we go back to the non-square, which is the square root, right? Remember why we squared in the first place. It's to get rid of the negative signs. But once you've done that, then you gotta neutralize the square. So you square first, and then you unsquare, or square root. So then the number becomes 7.18. So tip, for the same data set, the sample standard deviation was greater than the population standard deviation. And I touched on this, but let's formalize it. What's the logic? Since a sample is only a subset of all observations, there is more uncertainty or volatility associated with a sample, which is why the dispersion, or our estimate of uncertainty for sample, will always be greater than our estimate for uncertainty in the population.